All right, guys, we're going to go ahead and get started. If anyone hops in late, they can just kind of catch up with where we're at. Today, we are going to be working in the day, I believe it is 16. Just double check that. Yep, day 16, earthquakes and plate boundaries. Go ahead and share my screen so you guys can see that. Okay, so we're going to be working here. We got a little notes on earthquakes to start off, and then we're going to be doing a little mapping activity together as we go through. So go ahead and open up earthquakes so you can take the notes as we go through the lecture. All right. That's not what I wanted to do. All right, so let's talk about earthquakes. Stop that share and start a new share. All right, so first off, when we talk about earthquakes, what are we talking about? Well, an earthquake is defined as the shaking of the ground. And so what we're really talking about is we're talking about the study of seismology. Seismology is the branch of science that studies earthquakes. So we're going to be studying, why they occur, where they form, what they do to the earth as they send out their energy, and how we can record that. So where do earthquakes occur? Well, as we saw, the Earth's crust and upper mantle, the lithosphere, is broken up into those large chunks called tectonic plates. And we talked yesterday about how those plates are in motion because of the convection currents driving them in the mantle. So we know that movement is going to cause the Earth to grab, stress is going to build up, and then eventually that stress is going to become great enough that the pressure causes the Earth to move, and that creates earthquakes. So earthquakes are going to occur along plate boundaries, and earthquakes can create faults in the ground. So again, why do you think this might be? Well, all that motion, just think, the pieces of ground want to move, but they are locked together. That stress builds, and eventually stress becomes too much, and the earth moves and you get earthquakes, all that movement. So as tectonic plates push or pull or slip past each other, that creates stress. And like I said, the stress along faults near plate edges, that can create deformations. Deformations are going to be changes in the Earth's crust. That movement is going to change the shape, size, maybe composition of the rocks in some way, shape, or form. So it's going to deform the Earth's crust. Now, there are different types of deformation. There's plastic deformation and elastic deformation. So plastic deforms in a plastic manner. Remember, we talked about the asthenosphere, the second layer, as being a plastic layer, that slow moving solid. Think if you've ever worked with like real clay, like it's really hard. You can kind of move it. It doesn't break. It's not brittle, but it acts more like a solid, slow moving solid. So that's plastic. Plastic deformation is going to change what the layers of rock look like or layers of ground look like, but it does not necessarily lead to earthquakes because as it moves and as it's bent and stressed upon, it just kind of takes a new shape. Plastic deformation, new shape. Now, elastic deformation is a little bit different. Elastic, think like rubber band. And that rubber band, you can pull it and pull it and pull it and pull it and pull it, and eventually that rubber band will break and snap back to its original shape. That's elastic deformation. So rocks are the same way. They can stretch to a certain point. You can apply a little pressure to these rocks, but after a while, that rock, as that stress builds too much, is going to break, and then the rocks are going to slide back into their original places. And that does lead to earthquakes. It's that return to the normal position, that movement that creates the earthquake. So again, plastic is just going to kind of bend, it's malleable, it doesn't really break, so you're not going to create earthquakes. But elastic, you can add stress and add stress and add stress, but eventually it does break, returns to its original shape, just like a rubber band. It does create earthquakes. All right. So let's take a little bit closer look at elastic rebound. You need to come in. All right, so elastic rebound, like I said, is the sudden return of elastically deformed rock to its original shape. So think of as that moment when, if you're stretching a rubber band, that moment when it breaks, that's the elastic rebound as it shoots back to its normal shape and size. Same thing is happening to the rock. They build pressure, they build pressure, they build pressure, eventually they break. And when they break, they slide. And when they slide, that energy is released in seismic waves. Seismic waves. Earthquakes can happen at the Earth's surface, or they can happen deeper within the lithosphere. But again, most are occurring along plate boundaries. Later in the lesson, we're going to take a look at a map of the United States, and we're going to take a look at where recent earthquakes have occurred. Then we're also going to be taking a look at where the plate boundaries are located. And you will see most earthquakes do occur along plate boundaries, but there are a couple other things that we're doing, especially in the United States, things like fracking, if you've ever heard of that, that are really breaking up the ground. It's just kind of a mining for natural gas method, but it's really, really invasive on the ground. And what we're seeing is that this can actually lead to some decrease in stability of the ground in an area. And we have seen earthquakes start to occur in some of these regions. So we do have to be very careful about what we're doing. But most happen along the plate boundaries. Some can naturally happen in the middle of plates as well, just different stresses build up, but most along the plate boundaries. So like I said, when an earthquake occurs, it releases that energy through seismic waves. And those waves are going to travel through the Earth's interior. You guys saw this when we were doing the Earth's interior lesson, and we were looking at the shadow zones, right? Some of those waves that you already kind of talked about in there, you saw as they traveled through the Earth, they created shadows because they couldn't travel through like liquid, or they traveled a little bit slower through that semi-solid, things like that. And you guys should have seen that the speeds are going to differ a little bit as they go through these materials. So how fast the waves are traveling, again, is going to depend on whether it's moving through that solid layer like the lithosphere, the plastic layer like the asthenosphere, or deeper into the core like the outer core is liquid, and some things cannot move through liquid at all. So we're going to see how these different waves travel and reach their destinations. So first we're going to talk about the P wave. P stands for pressure. All right, these are pressure waves. They travel through all three states: solids, liquids, and gases. And P waves are actually the fastest moving waves. So as an earthquake occurs, that movement occurs, and it's going to release three different kinds of waves. P waves travel out fastest, so they're going to reach areas around the earthquake sooner. So if we want to do earthquake detection, a lot of earthquake detection systems try and read for these P waves. They are movement of the ground back and forth. Now you guys don't have a textbook, so don't worry about that figure, but it's just forward and backward movement. Okay, that's the P wave, forward and backward. And that's why it can actually travel so fast. So again, if we want to detect earthquakes and have earthquake warning systems in places, especially like California, P waves is what they're looking to detect. Now, P waves also don't really change the ground. They don't shake the ground that much. They're not the real destructive waves and movement or shaking of the ground that you think about when I say the word earthquake. They act a little bit differently. They're more subtle. But we can use the seismograms, things that measure earthquakes and the movement of the ground, in order to detect for these. And then that's how we can get the alerts out via cell phones or whatever it be. The second type of waves are S waves, and S waves, that S stands for shear, and they have more of like a side to side movement. Think of like how a snake slithers, that side to side movement. That's how S waves move. So P waves were forward and backward. S waves kind of go side to side. And they're created when the rock springs back to that normal position. Now, what's interesting is that these cannot travel through complete liquid layers. So, you know, S waves are not going to be able to travel past that outer core. And they're going to create some of those shadow zones because we cannot see the waves on the other side of the earth when they pass through that liquid. They just kind of get dissipated. That motion is lost. So these are kind of a medium speed, and they shake the ground a little bit more than the P waves. And last but not least, we have the surface waves. Surface waves produce motion in the upper few kilometers of the Earth's crust. When I say the word earthquake, the shaking that you're thinking of, when you visualize that in your mind, those are the surface waves. And there are two types. One produces up and down motion. So that's the up and down shaking, and the other produces the motion like the S waves. So together, it's more of almost like a rolling. And that is what really creates the damage that can happen to buildings and infrastructure like bridges and stuff like that. Because as the ground rolls, if the building is not built to withstand that motion, because most places are not, right? If we're building here in Indiana, I don't have to worry about earthquakes. So the building code doesn't require my building to be able to handle different kinds of motion that might occur during an earthquake. But if I'm building in a place like California, you better believe there is much, much more regulation about how my building or how my structure needs to be assembled so that it can handle these different types of motion and not collapse and not create all of that death and damage to our society. But like I said, kind of creates a rolling motion, and these move more slowly than the body waves. But these are the most destructive. These are going to create the most destruction to, again, think about all the stuff that we have in ground: pipes, gas lines, electrical wires. Now we have fiber optic wire in there. So all these things we want to protect, and we don't necessarily want them moving around so much. So we have to, again, be thoughtful about where we use these things and how we're using these things, especially if it's an area that has frequent earthquakes. All right, and that is it on earthquakes. Did you guys have any questions?
No.
Okay. So what we'll do now, if you guys would just flip over to the earthquakes locations, and you're going to have to open these up together. Okay, so open up earthquake locations and open up map 3. And go ahead and I think maybe it does, maybe it doesn't. I don't know if you guys have that installed. When you click on this picture, what comes up when it says open with? Does it say anything in the middle up here? Can you guys see my screen? So when you click on map 3, right? Click on map 3, this pops up. What does this show right here for you at the top middle?
Mine says open with, and then it has a line of .hub, cloud convert.
Okay, so you don't have that. All right, so let's see. We don't need that. Do me a favor on this one. Go ahead. It's going to ask you. It's just going to make a copy for you. Why is it? Go ahead and let's see. Because I need you to be able to like mark on this. And when I open it up as the file, it allowed me to do that on my computer, but it may not do it on here. Let me just try this real quick. I don't know if this will work, but we're going to try it anyway. Didn't even save there. Where did it save? In the pictures, maybe? No, I don't see it there either. Okay. Hmm. No, that would be why. Okay, so we're gonna have to amend this a little bit, probably. The struggles of teaching remotely. No. Let me try it one more way. Go ahead and open up Google. Go to images. I'm gonna have you try and find the image, and then maybe you'll be able to download it, and it'll open to something we can draw on. So we'll see. Let's see. You guys can still see my screen, correct?
Yeah.
Okay. Latitude, longitude, world map. So go ahead and type in latitude and longitude world map into Google Images. I'm gonna give this a shot anyway. And let's scroll down. Let's see if I can find the same one because it's a little bit clearer and easier to use. There it is. If you guys scroll down a little ways, you should see one that looks like this. It says World Longitude and Latitude Map. Hopefully you guys can find this one, maybe. Oh, that's not even the right one. That one's too small. Hang on. All right. That's the smaller one. I don't know if you find it, right click on it and go to save image as, and then just type world map. And it should pop up down here in your downloads. And let's try and, yeah, see, this one's way too small. All right, I want you to try one more thing. Go ahead and open it up on here, right? And what I want you to do, because you can't right click it, that doesn't work. I don't think you guys have that view. Do me a favor, open up a new tab. Sorry guys, bear with me. Open up a new tab, click on these little dots, and go to Drive. Okay. Does that map pop up anywhere up here for you guys as a recent thing that you used, maybe?
It's not popping up for me.
Okay, I didn't.
For me, but I'm on my own computer, not a school computer.
Yeah. Well, shucks. I don't know what to do here, because this is not going to work because we're supposed to plot these points. I'll tell you what we're going to do instead is you guys are going to read me the points. I'll plot them on my screen, and that way we'll at least be able to get through the activity together. Okay. And people, you guys will just have to, I'll leave it up so you guys can answer the questions while using that, but that's the best method I can think to do at this moment. So let me just download one. I thought there was a bigger one that I used. This is the bigger one. Yes, the bigger one. Okay, so we're just gonna save image as. Okay, open this. All right, and I will just go ahead and do this as we plot the points on here. This also isn't the right one, but that's okay. Doesn't matter. It does matter. I don't like all that extra stuff at the top. Let's use this. See what this does. I've already done this. I don't need to do this again. Yeah, thank you. Oh my goodness. You can have all my information. Just let me use your product. Oh my God, I don't need all this. Never mind. Never mind. This is not working. Mistakes were made. Last thing I'm gonna do. This will work. Just snip it and make my own picture. There we go. All right, I'll be able to draw on this. So that's what we're going to use. Okay. All right. So back to business. So if we take a look at the earthquake locations, what we're supposed to have been doing is I was going to have you guys mark some of the last major earthquakes on a map. And we were going to plot the points so that we could see these. And then we were going to compare them to where the plate lines are and things like that. So we're going to do some of these. We won't do them all, but I'm going to have you guys, I'm going to keep this up on my screen. And I'm going to have you guys read to me the different points and I'll plot them on here. Okay. So what is that first point?
40
40
degrees.
north. Oh, sorry.
You're fine. You can say it.
40 north and 125 west.
Okay, so if we're marking this, we've got 40 in the northern hemisphere. That's going to be this line along here. You said 121 west, you said?
125.
125 west, okay. So here's 110, here's 120, here's 130. So 125 is going to be right there. And I just lost where my mouse was. Hooray. This is a tiny little dot. And what we'll do is halfway in between those, we'll put a blue dot right there. Okay, we got our first one marked. Dylan, what's the second one?
22 degrees south, 180 east.
Okay, so 180 east is right on this line. And you said how many south?
22.
22. So again, where the heck is my mouse? Why is this so difficult to see? All right, 22 we'll say is right about there. This works much better in person, I promise. Okay, Mindy, next one.
She's probably muted.
All right, Dylan, give me the next one.
All right. 16 north, 96 west.
All right, 16 north. It's gonna be right about here. You said 96 west.
Yes, 96 west.
All right, 96 west. So we got to come all the way over here. I can't see where the damn thing is. This is really frustrating. Can I make it different size? All right, there we go. Now I can see it a little bit better. All right, you said 16 and 96 west. So there's 90, there's 100, there's 16. So right down, we'll say right about there. Right. Yep. Okay. Next point.
38 north and 20 east.
38 north and 28 east. All right. Right there. Okay, next point.
55 south, 119 west.
55 south, 119 west. Okay. Next point.
3 south, 153 east.
All right, that's right about here. Okay, next point.
34 north, 118 west.
118, 34. Okay. Next one.
45 north, 148 east.
148 east, 45 north, right about here. Okay. Next point.
We already did the 39 north one, right? Or was it 45 north?
That one was 45 north.
Okay, 39 north, 141 east.
141. Okay, right down here. Hey, look, two real close to each other. Must be near a fault line. All right, next one.
11 south, 163 east.
163 east and 1 south. Oh, that's real close to this one. All right, we kind of already have a dot there, so we'll leave it there. Next one.
13 south, 71 west.
13 south, 71 west. Right about there. Okay. Next one.
51 north, 179 west.
179. That's right about here. Okay. Next one.
44 north, 129 west.
129. Okay. All right. Next one.
1 south, 100 east.
100 east. Right. That line. Right about there. Okay.
25 south, 176 west.
25 south. You said 176 west?
Yep.
Okay. That's right about there. Next one.
24 north, 94 east.
24 north and 94 east. All right. Right about there. Next one.
0 and 18 west.
18 west. Okay. Next one.
7 south, 126 east.
126. Okay. Right in there. All right. We'll do two more.
28 north, 140 east.
40 right on that line. Okay. And Mindy, what's the last one for us? Last one.
37 north and 71 east.
71 east. Okay. There we go. All right. So we can start to see that some of these dots look to be kind of in line with the others. Okay. If we look over here, I'll use a different color. If I'm looking over here, let's do, okay. So if I'm looking in this area, oh, it's still blue, it's okay. This is the fault line that we have on the west coast of the United States that creates the San Andreas Fault. So if you guys would, I'm gonna leave this up on the screen and I'll put it back up on the screen in a minute. But go ahead and scroll down real quick and let's look at this map right here. It says plate map with volcanoes. All those dark lines that you guys see, those are all the different plate boundaries. And all those little red dots that you see are volcanoes. So this is one of the reasons that this is called the area around the Pacific coast is called the Ring of Fire. And we can see, you know, all up and down along Japan is really on that fault line right there. And then again, on the West Coast, like we were talking about, you can see that fault line just kind of cuts through certain parts of California. So if we go back and I bring up the map that we put together, we can see some of these areas. Now our maps are oriented a little bit differently. What's really hard about this is the ring of fire itself is really spread out. So that's part of it. And then it comes on the other side of the map. If I can figure out, okay. So this is that ring of fire. So if we were to like kind of turn this around or reorient the map, you guys would see that that ring of fire is right there. And then a lot of those volcanoes and a lot of those earthquakes are happening along the same areas. Obviously my line cut too far in for where the fault lines are, but you guys can kind of get the idea of where that ring of fire is really occurring, okay? So I'm gonna leave this map up so you guys can use this for reference. I'll put it back up here in a second. But what I would like you guys to do now is just go ahead and answer the questions. There's only 6 of them, and it shouldn't take you very long. And this is what I want you guys to turn in for your exit ticket for today. So they'll still be in place of the exit ticket. So go ahead, answer these questions. They shouldn't be too hard based off of, like the notes and the activity that we did and kind of analyzing the 2 maps that you have up. But let me bring that back up. All right, and I'll leave this map up so you guys can, hopefully I can stop drawing. There we go. You guys have a nice and center view of it. And I'll leave this up, like I said, there's not much more from me today. So if you guys have any questions, just chime in, but otherwise I'm going to mute myself and let you guys complete your work. And when you're finished, feel free to log off and I'll know you're done. And just make sure you do submit that in to me, okay? Any questions before I mute?
No, all good.
Nope.
Well, thank you guys for bearing with the technical difficulties of teaching remotely. Hopefully this won't be forever.
Hopefully.
All right, so good luck with your work, and then just again, hop in and ask a question if you need it.
Did you say there was an exit ticket?
No, I said I wanted you to turn this in instead of an exit ticket. So once you're done the questions, I'm just going to use that as kind of your exit ticket for today.
Oh, okay. Well, then I'm done. All right.
All right. Thanks for zooming in.
No problem.